Hello everyone, in this video we are going to go through details of an example of analyzing a system in the frequency domain. Here we have a standard feedback loop with the controller being equal to 1, so GC is equal to 1, and GP is equal to 1 plus 10s over the denominator. Basically there are 1, 2, 3, 4 poles and 1, 0. The 0 is located at minus 0.1 and the poles are located at 0, minus 1, minus 10 and minus 10. Now we need to go through these steps. We need to draw the asymptotic body diagram and then we'll compute omega c and phase margin from the drawing and verify that the closed loop system is bistable. And after that we will discuss about the noise attenuation and disturbance rejection properties, and at the last step we will check the overshoot and settling time based on the approximations that we have. So let's start by constructing our L of j omega, which will be equal to GC times GP. GC is equal to 1, so we'll have 1 plus j 10 omega over j omega times 1 plus j omega times 1 plus j omega over 10 squared. So the components that we have here are 1 plus j 10 omega, 1 over j omega, 1 over 1 plus j omega, and 1 over 1 plus j omega over 10 squared. Let's start to draw the body plot for this system. Here we will have the amplitude, and the phase. Let's assume that here we have the frequency of 1, 10, 100, 10 to the power of 3, and 0.1, 0.01, 0.001, and so on and so forth. And similarly for the phase plot. Let's go through the components one by one. The first component is 1 plus j 10 omega. It's a 0 which is located at minus 0.1. So the corner frequency for the 0 will be equal to 0.1. Approximate amplitude plot will be like this. So it will be 0 dB until that frequency. And if I say that here we have 20, 40, 60, 80, 100, we will have a straight line from 0.1 upwards with the slope of 20 dB per decade. So we will have a line like this, which has 20 decibel per decade as the slope, and it is for our 0, 1 plus j 10 omega. The next component to consider is 1 over j omega. So up to omega equal to 1, we will have, indeed it's a pole right at the origin. So we'll have a straight line with the slope of minus 20 decibel per decade. And it will cross the 0 dB at omega equal to 1. So we will have minus 20 dB here, minus 40 dB, 20 dB, and 40 dB. So we will have basically a straight line. If I can draw it without using a ruler, it will be something like this. So this is with minus 20 dB per decade, and that's for our 1 over j omega. The next component is 1 over 1 plus j omega. For that component, the amplitude till omega equal to 1 will be 0. And after that, we will have minus 20 decibel per decade. So we have the same slope that we had for the pole at the origin, this time for 1 over 1 plus j omega. And the last component is 1 over 1 plus j omega over 10 squared. So we will have up to the frequency of 10, we will have 0 decibel approximately. After that, we will have minus 40 dB per decade. So at this point, we will have minus 40. At omega equal to 10 to the power of 3, we will have minus 80, and this will be our last component. So minus 40 dB per decade. And now we need to combine all these with each other in order to obtain the overall body plot for the system. Let me change the color. Okay. So up to omega equal to 0.1, we will have the contribution coming only from the pole at the origin. After that, we will up to omega equal to 1. The 20 dB per decade slope will be cancelled by minus 20 dB per decade that we have from the pole, and as a result, we will have kind of 0 dB per decade. Then we will have another minus 20 dB per decade introduced by this component here. So overall, we will have minus 20 decibel per decade after this point. So around omega equal to 10, approximately, we will have 0 dB. And after that, we will have minus 40 dB per decade added to our slope. So in total, we will have minus 60 decibel per decade. At omega equal to 100, we will have minus 60. And at omega equal to 10 to the power of 3, we will have minus 120. So the approximate body plot will be like this, where here we have minus 60 decibel per decade. So the approximate body plot for the system will look like this one. And this is for the amplitude only. Then we can check what we have for the phase. Again, we will start with the first component, which is 1 plus j 10 omega. If I assume that here we have pi over 2 pi, 3 pi over 2 and 2 pi, and the negative values here. For the 0 as the first component, we will have 0 degrees initially, or 0 radians. And at omega equal to 0.1, which is this point, we will have pi over 4. At omega equal to 1, we will have pi over 2, and then approximately it will remain as pi. So this will be the phase plot for the first component. For the second component, it's easy. We have the pole at the origin, so the phase will be equal to minus pi over 2 all the time. For the third one, we have 1 over 1 plus j omega. At omega equal to 1, we will have minus pi over 4. 1 decade later, it will become equal to minus pi, and it will remain as minus pi. And approximately 1 decade before, it will be equal to 0. So this will be the approximate phase for this component. And finally, for the last component, we have two poles at omega equal to 10, s equal to 10, which is over here. 1 decade before, the phase will be 0. 1 decade after omega equal to 10, which is omega equal to 100, the phase will be 2 times minus pi, so minus pi over 2, so we'll have minus pi. And at omega equal to 10, we will have minus pi over 2. And now we need to add all these together. It means that initially we will have minus pi over 2 up to this frequency, which is 0.01. Then the phase will increase a little bit as the result of the introduction of the 0. And then we will have the pole contribution, the third component over here, will start to decrease the phase. And at the same time, we have some contribution from the 0. So basically, the phase will remain somehow constant. And after that, we will have the final component affecting the phase of the system, which are the two poles at omega equal to 10. And you can, from this point onwards, you can see that the pole, the 0 that we have, the phase of the 0 that we have, is cancelled by the 0 of the pole at the origin. So only the three components will affect the phase of the system, and therefore the phase will start to decrease. At omega equal to 10, we will have almost minus pi, and I'm saying almost because it is not, this is not the exact drawing. And at omega equal to 100, we will have minus pi over 2, which is minus 3 pi over 2. And then the phase will remain constant. So this is the approximate phase plot for this system, together with the approximate amplitude plot that we have drawn. Now, we need to compute omega c and phase margin from the drawing and verify that the closed loop system is stable. It will be a little bit tricky for this example because we haven't drawn it using the proper, let's say, scaling. However, if you look here, you can see that the crossover frequency will be somewhere around 10. So we already discussed that the crossover frequency will be around here, because there we have the amplitude plot crossing the 0 dB. So omega c will be around 10. We will get the exact value. And in terms of the, let's say, the phase margin and the gain margin, we need to find out the exact value indeed for omega c. Then we will come back here and check the difference between minus pi and the phase. This will give us the phase margin. And then we need to find out the exact frequency where we have frequency equal to minus pi. We'll go back to the amplitude plot and find out the gain margin. Okay, so let's plot the body plot for the system using Matlab. I have the system declared here in the form of a zero pole k, 0 pole and the gain ZPK. We have 0 at minus 0.1. The poles are here, and as for the gain, we have 1000. So this is important to keep in mind that in this format we will have gain equal to 1000. Using the margin command, we can plot the body diagram, and at the same time we will have the gain margin and phase margin shown on the graph. So here you can see them. We have the gain margin equal to 7.52 at the frequency 10.9, and the phase margin is equal to 29.3 degrees at the frequency 6.78. You can see that the body plot that we have here for L of j omega is somehow similar to the one that we have obtained over here. You can compare them indeed. And the phase finally goes towards minus 270. It starts from minus 90 degrees. So basically it is quite similar. The tricky point is to find out the crossover frequencies. If you want to find the exact one, you need to apply the amplitude of L of j omega equal to 1 or 0 dB and find out the crossover frequency, and then you can find the phase margin. So we have the crossover frequency equal to 6.78 radians. So the exact omega c is equal to 6.78 radian per second. And the phase margin is 29.3 degrees. Phase margin is 29.3 degrees. For the gain margin, the frequency at which we have calculated the gain margin is 10.9. Oops, this is the frequency. The phase crossover frequency, we call it CP. It's equal to 10.9 radians, and the gain margin is 7.52 decibel. 7.52. And we can see that the closed loop system will be stable. Closed loop is stable. Indeed, we can form the closed loop system and draw the step response for it, and we will see that the closed loop system is stable. So T will be equal to feedback of Gm1. So G is equal to our L indeed here. And then we will have figure and step of T. And hopefully our closed loop system will be, you can see the transfer function, and here is the step response of the system, and you can see that it is stable. Now, as the next points, we need to check to find the minimum frequency such that for the closed loop system, we have an attenuation of 100 times for the noise signal on the output. So gamma n is equal to 0.01, and we want to find out the proper omega n, for which range of frequencies the 100 times attenuation of the noise will be the case. So basically we need to find out where the amplitude of L of j omega falls below minus 40 decibels. We need to come to the body plot that we have for L of j omega, draw a line at minus 40 decibel, and find the frequency at which the amplitude goes below that value, and this will give us the omega n. So it will be somewhere between 10 and 100 according to our drawing, or it might be pretty close to the 100 radian per second. Let's go back to the body plot that we have here. We need to find out the frequency at which amplitude goes below minus 40. We are kind of close to it, minus 40.7. So the frequency will be around 46. Omega n will be around 46 radian per second. After that frequency, the amplitude of L of j omega will fall below minus 40 dB, and therefore the 100 times noise attenuation will happen. The next point is regarding finding the frequency, the maximum frequency, such that for the closed loop system we have an attenuation of 100 times for the disturbance signal on the output. Gamma d is equal to 0.01. We need to find out omega d. Since gamma d is equal to 0.01, we need to find where amplitude of L of j omega, the range of frequencies for which the amplitude is bigger than 40 decibels. Again, we need to refer to our body plot that we have, draw a line where we have the amplitude equal to 40 dB, and then for find the frequency for which the amplitude remains above that 40 decibel. And from what I see over here, it will be some frequency a bit smaller than 0.01. You can refer to the body plot that we have here. Let's see if this is close. So we have 39.8, pretty close to what we are looking, so to 40 dB. As a result, the frequency will be equal to 0.0102. So omega d will be equal to 0.0102 radian per second. So in this way, we have found the frequency. If the disturbance signal has components below this frequency, they will be attenuated by at least 100 times. But if the disturbance has frequency components with a frequency bigger than the value that we have obtained, they will not be attenuated by 100 times, but they will be attenuated by a smaller factor. The last point is to estimate MP and the settling time, the overshoot and settling time for the closed loop system, only using the information that we have from the body diagram. Referring to the body diagram, we have the omega c and the phase margin. We just wrote them here. So omega c is equal to 6.78. Phase margin is 29.3. Phase margin is smaller than 75 degrees. So we will use the second order approximation. For our second order approximation, omega n will be approximated as omega c. Let me rewrite this. Omega n will be approximated as omega c, and the zeta will be equal to phase margin over 100. So omega n will be equal to 6.78 and zeta will be equal to 0.293. Having these values, now we can calculate the value for the overshoot, for MP, not PM. For the overshoot, and also the settling time. You just need to plug the values into the formulas that we have for MP and the settling time. I would like you to do that indeed, to plug the numerical values into the formulas and obtain them, and then compare them with the values that we have here. So over here we will have the peak response, which will be around 35%, 35.3, and we will have the settling time around 16 seconds, 15.5 seconds. Okay, so I would like you to find out those values. Just plug the values into the formulas and obtain the estimates and compare them with the actual values that we have for the closed loop system. Alright, so I think that's all for this video. I hope you have got the points of how we can refer to the body plot of a system and discuss about the stability of the closed loop system, and also have some estimations in terms of the step response parameters. Thank you for watching, and see you in the next video.